introduction, and today we'll be talking about an overview of wireless communication systems. We'll go over like historically a little bit. Wireless communication started historically how, and then just a quick journey from history to future, including the current state, and then we will go in a slower pace on the challenges facing wireless communication systems, what they are trying to solve, and then the current and emerging wireless communication systems in details. Why do we describe the technology? Why do we need to go through that? Because without understanding the main technology that we are targeting or the main systems, we wouldn't really be able to analyze and understand the security risks and security solutions associated with those systems. Might be that some of this information you have seen it before in your communications course, but I guarantee you there are some other parts that you haven't seen before. Okay, history. So wireless communication is very ancient. People started trying to communicate together by using smoke signals. So they stand at further away locations where they cannot hear each other, but they agree on a particular code, and then they hide and release a bit of smoke, and then cover the fire and release another bit of smoke. And when you see a certain pattern, it means that person is asking or sending a particular message. This evolved eventually in the modern era of wireless communication to the telegraph dot and dashes that you can send through cutting and connecting electric signals across wires, and then wirelessly later on. Right? If people want to communicate, that's a bit of an advancement. If they want to communicate wirelessly for much longer distance that are not visually, does not require visual contact, because the case of smoke signals requires some visual contact, and also to carry larger messages, they used to use some animals to do that. Particularly pigeons are very famous for being used to send messages wirelessly, because you do not have a wire between one person and the other. But then the actual or the real wireless that we are talking about when we say wireless in our nowadays started in the almost towards the end of the 19th century, so 1880, where Marconi did the first wireless transmission. It was wireless transmission of telegraph signal. So you do the tit, 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 and so on, but it gets transmitted wirelessly without being connected between the sender and the receiver. Marconi is an Italian guy, by the way, and then this evolved into what we see nowadays. Okay, one important thing, and it does not only apply to wireless, even though it has a special case for wireless and particularly wireless security, but human beings are well known to develop much better technologies and emerge with a lot of advancements in science and technology when they face war. And World War II particularly was the time where a lot of advancement in telecommunication happened, particularly wireless communication. Why war has such an effect on wireless communication? Because by nature in war you have troops or armies that are going into unknown areas. Eventually they get spread around that area, and to coordinate and to manage the attacks in a correct way, they need to communicate together. Not only that, they need to communicate together, of course, wirelessly, because they do not have the luxury of digging and connecting wires. But they also want to make sure that this wireless communication is not intercepted by the enemy. You don't want the enemy to know what you are talking about, what are your plans, what is your next step, right? But you still want to communicate this to the rest of your army. So this is where also security of wireless communication or of communication in general came into the picture. A disclaimer, some of the numbers in these slides are a bit outdated, because these slides are they are from a book, and the book is, I think it's 2013, 14 publishing time. The first slide had the name of the book, in case you want to refer to that book. So for example, it says that the number of users is right now is 8 billion worldwide. This is a little bit of an outdated number. By the way, when we say 8 billion, it doesn't mean that they have to be 8 billion human beings, right? This is the number of, for example, here in Qatar, the number of cell phones is like double the number of the population of the country, because many people carry 2 or 3. There are people who are using the wireless connection not for themselves, but like a SIM card for their iPad or for their whatever connected to the network. So this is kind of what we call the number of users. It's just a number of authorized users. Doesn't have to be different individuals, okay? So not only cellular, so typically for connectivity nowadays, we use the cellular technology, but that's typically when you go outdoor. Most of the time when you are indoor in a confined area, we tend to use Wi-Fi. So that's another technology that is actually key backbone technology for what we are doing nowadays in wireless. We also have Bluetooth and satellite. So Bluetooth is for short range communication. And the nice thing about Bluetooth, it can be considered as a replacement of a wire connection between a device and another within a short distance, typically 10 meters or less. We will have a slide specifically about Bluetooth in terms of the cons and pros of the technology. But also when we want to cover a much wider area, then we go also to satellite communication, which is also something widely spread nowadays, specifically with the new era of Starlink and all these new technologies using satellites, okay? So these are kind of the key technologies. Cellular, Wi-Fi for indoor, cellular for outdoor. If you want to do a very big coverage, satellite is the solution that you go to. And if you want to do very short communication, most commonly nowadays we use Bluetooth. There are other emerging technologies that competes with Bluetooth. We will discuss them when we reach that point. So what is pushing the communication system from the historic to the current to the future? What are the key factors that are affecting how we will evolve in communication system? 2 keywords. Ubiquity, so you want to establish ubiquitous, yeah. Connection. You want to stay connected all the time. The word ubiquitous means always there, no matter where you go, okay? That's one key factor. And the other key factor is everything is talking to everything, which is nowadays called the Internet of Things. That means that we are no longer confined to human talking to a human. We have now human talking to a human, human talking to a machine, machine talking to a machine, right? And many different types of machines. So a fridge talking to your cell phone, lamp, you control it through Siri on your cell phone and so on, right? So everyone is talking to everyone. That's called the heterogeneity of the connection. So we have many types of connections and many type of end points for those connections. Devices, people, machines, whatever, cars, right? All of that, you want to connect them together. So these are the 2 pushing factors, right? You want the connection to be always there. That's the ubiquity of connectivity. And you want everyone to be able to talk to everyone, which means different types and different characteristics of users connecting together. That's called the heterogeneity of the network. Under those 2, there are many things that are pushing the advancement of wireless communication. I mean, application-specific things like vehicular networks, that's automated highways, smart homes, sensor networks. So you want to kind of read what's happening on a particular domain and send that information to another location. Multimedia, you want to exchange not only text or voice, you want to exchange video, audio, everything, right? So that's also and the internet access that everyone wants to have access to. So these are kind of details, but the major drivers, as I mentioned, the 2 drivers, if you remember them, what were they? Anyone remembers what were the 2 drivers of advancement? You can say them in any words. It doesn't have to be the key words that I mentioned.
To be always there, and also to communicate with everyone.
Yeah, so the Internet of Everything, or the connectivity between different types and always connected. Yeah, okay? We call those ubiquity and heterogeneity of the network. Okay, challenges facing wireless communication specifically can be categorized into two categories. Challenges that are induced and exist in the network itself, especially the radio communication in the network, so the connectivity itself. And the other thing is challenges associated with devices, okay? Sometimes it's not the device, but a smaller level inside the device, which is the chips. So SoC is system on chip, and these are challenges at the chip level. Nowadays, most of the functionalities performed by your phone are put into one chip. Earlier technologies, like 15 years ago, used to be multiple chips on a board. Now, most of the functionalities are gathered into one chip, and that's what's called a system on chip, okay? If you go to the network, you will find that your objective in general for a wireless communication system or for a communication system in general is to send the highest rate with the highest reliability, so no error, using the minimum possible energy. So you always want to achieve that triangle. Unfortunately, these things, if you gain in two of them, you have to pay on the third, right? So you cannot achieve good, I mean not good, optimum in all of them. You have to pay the price in one of them, and you can gain in the other two, okay? What are these three key factors? Rate, you want always to increase the rate as much as possible. Error, you want to decrease the error as much as possible. So ideally, no errors, but that cannot be achieved. And energy, you want to decrease the energy consumption as much as possible, okay? So decrease, increase, okay? These three objectives together cannot be achieved at the same time. You have to sacrifice one to gain in the other two. Okay? Sometimes even you sacrifice two, but the key idea is you cannot achieve the three of them at the same time, okay? Depends on your application and which one is more important for you. You decide which one to sacrifice and which ones to gain on, okay? Yes? Energy?
Yeah.
Energy efficiency? Third, I'm coming to it. I didn't mention it yet. I just talked about the first three keywords, so data rate, error, and energy, okay? Another challenge, which is different from those three main objectives that I mentioned, is the scarcity of the spectrum. It means that we don't have available frequency ranges for us to use nowadays as compared to when wireless communication was invented in the 1880s, right? Nowadays, almost all the available frequencies are used by someone. So whenever you want to introduce a new user to the system or a new technology to the system, it's very challenging to find available frequency for you to use, okay? That's called the scarcity of the spectrum. It's very similar, can think of the spectrum as a real estate, right? So similar to if you want to buy a land in Doha, probably you'll not find. Everyone has already captured the land that's available inside Doha. You have to probably go for another city to find some available land for you to buy. Similarly, if you want to put your system in a particular frequency range, you will find, oh, if I want to put it here, sorry, this is already allocated to Ooredoo. I want to put it here, sorry, it's already allocated to TV. I want to put it here, sorry, already allocated to satellite communication. So it's challenging to actually find a particular spectrum, a particular frequency range for your system to use for wireless communication. That's called the scarcity of the spectrum, okay? Another important challenge as well is coverage. You want the connectivity to stay on all the time. So we face this, particularly in this new engineering building. You move in some places and then your cell phone gets out of service. It can no longer see any signal received on your cell phone. That's called the coverage. And we want the coverage to be as reliable as possible, which means that I want to be covered all the time. I don't want my cell phone, that's my desire, right? Is it doable or not? That's a challenge, okay? And as I mentioned, this one we already talked about, the heterogeneity of the network that comes from the connection between different types of devices and different types of users, and the staying connected all the time that we mentioned, the ubiquity, it's seamless inter-networking handoff. So I move from one location to the other, from inside the building to outside the building. I can have some service inside the building using Wi-Fi. If I go outside, I no longer can reach the Wi-Fi, but immediately I connect to the 5G system or the 4G system outside, right? I move from this to go into an aeroplane. I'm supposed to have some Wi-Fi inside the aeroplane and so on. So we want to maintain that seamless move from one technology to the other. The major factor is, again, the desire to stay connected all the time without feeling any interruption, okay? That's on the network side. On the device side, you want your device to be performing very well, so you want it to be really fast and responsive. If you have a very old technology device and you say call, and then it stays for 2-3 seconds until it brings you the keypad or brings you the contacts, and then you choose a contact until it brings you the number and rings the phone, it takes another 5 seconds, then this is not what you want, right? You want really a device with good performance. So that's number one. But at the same time, you want it to be as cheap as possible, which means that it cannot be complex. Because complexity means more components, and more components means higher cost, right? So even though you want it to perform well, but the opposite thing is you want it to be also affordable, not really very expensive, right? And then comes the combination of you want it to be light, you want it to consume less power, and the cost which is associated with complexity. So as small as possible, but if it's too small, I cannot see the screen. As light as possible, but if it's very light, you probably will not have enough battery capacity in this device, so it will not stay powered on for a long time. So always contradiction, right? Whatever you are, this is why these things are challenges, right? You want it also to be able to use higher frequencies. Why higher frequencies? This goes back to the scarcity of the spectrum. All the lower frequencies are already used by someone, right? So the only available frequencies now are very high frequencies, but very high frequencies are challenging to implement in a device. They require higher cost components, and sometimes they are beyond the current technology. You cannot do them with the current technology. You have to wait for the next generation of electronics to be able to achieve or manufacture those devices, okay? Multi-radio integration. So that has to do with the seamless connectivity. This single device can connect to Wi-Fi, which is a technology. It can use Bluetooth, which is another technology. It can use the cellular 4G or 5G, which is a third technology. Nowadays, also, most of them have near-field communication. So you can do tap, those payments and stuff. This is another wireless connectivity. By the way, sometimes they tell you Wi-Fi, it's not Wi-Fi. Okay, so when you go to a store or something, it says you can pay by Wi-Fi. This is not Wi-Fi. This is called near-field radio communication. Totally different from Wi-Fi, okay? So all of these technologies used to be in the past separate from each other, right? You can only have your laptop connecting to Wi-Fi and that's it. You can only have a cell phone which is using the GSM, which is the cellular network, and that's it. Does not do much. And then later on, Bluetooth became on everywhere, and then later on, Wi-Fi became everywhere, and so on, right? And then now we have all these with the near-field communication as well. So that's another desire. Last but not least, many of these devices are now able to connect to the Wi-Fi and to the network at the same time. They are at the same place. I have my phone, my iPad, you have all your devices, your phones, and we are all able to connect at the same time. This is called coexistence, right? That's another challenge that these devices have to handle when designed and manufactured, okay? This is just a list of challenges. How they are addressed, it's a totally different story, okay? Each one of those requires like 6-7 lectures just to describe the technologies that are used to address any of these, okay? I'm not gonna touch upon them, but just to keep in mind what are the things that when a manufacturer of a device is looking to have a good device, what are the things that they keep in mind when they are designing this? And not only the device, but if you want to connect these devices together, what are the things that the network designer is looking for to make sure that they can achieve or that they can do their best to achieve, okay? Coming back to a little bit more details about that spectrum scarcity challenge, this is a chart developed by the FCC. FCC is the Federal Communication, I don't remember what's the term, Federal Communication Council, maybe, I don't remember. But that's the entity in US which is responsible for managing the spectrum. You can think of them as, similarly here we have the CRA. And you can think of those two entities as البلدية, which is managing the allocation of lands. Who gets which piece of land and who can buy where, right? And who can build where. Similarly, for the range of frequencies available for communication, the FCC regulatory or the CRA here in Qatar are responsible for saying this particular entity owns that particular spectrum. This particular technology works only in this particular range of frequency, okay? They issued a study. It's an old study because the book is old, and this study is from the book. You can see it stops at 2014, but the same trend is ongoing. So you can see that earlier in 2009, right, there was kind of a growth of the mobile data, so the usage of the system. More users, more devices connecting, and then accordingly, the usage of data transmission over the wireless network has been increasing with those ratios that you see here. Correspondingly, the usage of the available bandwidth was kind of getting into a problem. So what this second chart shows you that if you go to 2009, you will see that the total required spectrum compared to the total available spectrum was at a surplus. So the total required was less than the total available. By how much? By approximately 400 megahertz, or specifically 377, right? So the total demand on bandwidth was less than the total available bandwidth by this amount in 2009.
The available ones.
Hmm?
The available ones.
The non-used one, available but non-used, is this amount, okay, which is the difference between offered range of frequency and required range of frequency, okay? As we go through the years, this has been less and less, and then around 2013, 2014, we started flipping. So the total required bandwidth was more than the available bandwidth by 90 megahertz, and then it became by 275, so deficit. So we need more, but it's not available anymore. Now, if you look at this figure and you extend it through the current years, you will see that it's going the same way with more growth, so more negative demand because the requirement was going much higher with higher range. But then new technologies are introduced like the millimeter wave. So you have some more availability, so it shrinks back or goes to a surplus momentarily, so for a couple of years, and then it goes into the deficit again. So we introduced new range of frequencies that was not used before because the technology was not able to use it. But then as soon as we introduce it, the usages becomes very quickly increasing until we consume that as well and we wait for another technology. The two key technologies introduced in the last couple of decades were the millimeter wave. Millimeter wave was expected to be integrated within 5G, but this did not happen. Just hopeful, but it didn't happen. Because of lack of technology, because of many challenges meeting or facing millimeter wave, even though it can have very high transmission rate, but it faces the issue of being highly absorbed by water vapor and oxygen in the atmosphere. So you communicate and your power decays very quickly, gets absorbed by oxygen and water vapor in the atmosphere. So you cannot really communicate over a large range unless you inject a lot of power, and nobody wants to do that, right? So that's a challenge being addressed by the technology, but not yet complete. However, I was in the conference last week where I missed your lecture, and in that conference, Ooredoo showed a demo that they have already installed millimeter wave in some of the highly dense areas like airport, so the Hamad Airport, some of the bigger malls, the high-end malls, like they don't want me to mention which ones, but anyways, but even though they installed the infrastructure for that and they showed us a demo, but the devices that we have at hand nowadays are not yet licensed to work with millimeter wave inside Qatar. So even if you buy a cell phone, from Qatar, the millimeter wave is not enabled on that device. If you buy it from North America, for example, millimeter wave circuitry is implemented, But the software, as soon as you get into the region of Qatar, disables that because of licensing issues, right? But soon the licensing is going to be available, and the devices, the newer generations of the devices, as well as the other brands in the market, are going to use that. And then they will be able to cover for places where you have too many people using the system. Typically, for example, if you notice, if you go to a very crowded mall in the current system, sometimes you try to call, it just gives you busy signal, right? This is not because the other party is busy, this is because the network is already full of users. So it cannot support any more users, right? Or you try your data connectivity, and for some reason you are connected to the Wi-Fi, but there's no download. It's not because the server has a problem, it's because the current network inside that place is already fully utilized. So it cannot really serve your request.
What's the characteristics of this millimeter wave? And what's the difference between it and normal waves?
It's much higher frequency. So it goes to the sub-terahertz, so up to 300 gigahertz approximately. Yeah, above the 6 gig. So typically we work in the current technologies that are not millimeter wave, we work until until 6 gigahertz, 5 to 6 gigahertz. Now if you go above that, typically 30, 60, 90, up to 300 gigahertz. That's a higher frequency, requires more advanced electronics, but because when you go to higher frequency, you can have more transmission rate. You can transmit with a much higher rate because you have a more available bandwidth at those higher frequencies, right? So that's why it's nice from that perspective. The disadvantage is they can only travel for short distance before their power gets completely absorbed. That's the main disadvantage. And they require line of sight, so they do not do nice penetration of walls or ceilings or things like that. So these are the two challenges of the millimeter wave. Now, the other technology, now millimeter wave has been moved somehow to 6G, so it did not get implemented really in 5G except for trials and stuff like that. But the next technology as well is terahertz, which is from above 300 gig until 10 tera, right? That's the end of the RF, and then at that point you start dealing with optical, you start dealing with infrared, and then visible light, and then so that's the end of RF. So nothing higher than that can be considered RF communication anymore. Becomes optical communication, okay? That part, the terahertz, is currently being utilized or thought of as being utilized when the technology is mature enough for that, to do connectivity between devices, particularly in things like data centers, where you have too many computers connecting to storage devices within the same room. So rather than doing cabling using fiber or any other type of cabling, they can just talk to each other with terahertz communication. Very high rate, but the distance gets even shorter. So it becomes very similar to light. So you can see that light really cannot travel for a very long distance unless you inject a lot of power to it, and it cannot penetrate any obstacles, right? So that's kind of the trend going in that direction, okay?
And to use like the spectrum, if it's fully occupied, do they do like, as we studied before, like orthogonality or something?
Yeah, they do some techniques, yes. So the story here is about after doing those techniques, there are no more availability. But yes, you can do things like time sharing, so you allow everyone a time slot different from the other, or you can do something like using multi-antenna technology, so they become really not interfering with each other, using the same frequency and communicating at the same time, or something like CDMA, like the spread spectrum communication. There are many technologies that allows you to do simultaneous communication, but again, each one of those has a maximum limit after which you need to go to another frequency. Okay. Yeah. Okay. Current and next generation wireless systems. So again, these are outdated. So the current is no longer 4G. It's actually 5G. But anyways, 4G/5G cellular systems. This is not a conventional naming. So we are now at the 4th generation or the 5th generation of wireless LAN or Wi-Fi. But we don't call it 4G. Typically, we just refer to the standard with some letters. So now we have 802.11a, C, and we have also 802.11n. That's a current technology. There are more futuristic ones coming out of the Wi-Fi, more bandwidth, more capabilities, more number of users. millimeter wave and massive MIMO systems. These are currently being deployed, but on the massive MIMO are deployed in systems. Millimeter wave is on trials, so it can be considered as current / slightly futuristic. Satellite, of course, Bluetooth, Zigbee, and gig Wi-Fi with gigabits per second rate. All of these are more or less current available technologies. The emerging one is no longer 6G, it's 5G, it's actually 6G. The usability of, or the utilization of visible light communication. So they call that Li-Fi. It's like wireless network, but using light. So they call it LI, like stands for light, Li-Fi. Instead of Wi-Fi, which is wireless fidelity, it's light fidelity. These are already developed as technologies. There are many manufacturers for those, but in terms of making it to the market, the current usages are going to be something like connectivity inside a single room, or more prominently, it's going to be utilized on transportation, inside transportation systems. So inside high-speed trains, inside airplanes, your devices are going to communicate to the network of outside the aeroplane through light communication inside the aeroplane. Why they like light communication in that case? It provides very high speed, because light is a very high frequency signal, and more importantly, does not interfere with the aeroplane navigation system. So you don't have, in that case, to be told that you have to switch your phone to aeroplane and do this and do that while taking off and landing, because when you use light, you are not interfering at all with the communication of the aeroplane. You are in a completely different domain of communication. Okay, so that's why these technologies are thought of as being useful in these cases. Ad hoc and cognitive radio, we'll describe a little bit more details about that, but the summary is these are smarter networks that, in the case of ad hoc, they do not require a pre-designed infrastructure. So now to connect to Wi-Fi, we know that there is a fixed access point here, and whenever you come to the room, your device connects to the access point, and then the access point takes the signal and sends it to whatever destination you want to communicate with. The same thing happens in the cellular network. So wherever you are communicating with a particular base station, and then the base station is responsible for taking the signal and sending wherever you want to communicate. Now, in the ad hoc case, this is not the case. We just come into this room, we have a few devices, there's no access point, nothing. Our devices just start talking to each other, and they establish communication between them. That's why we call it ad hoc. And then anyone can leave the room, so the network will come with less number of users. Any 2 or 3 more people can come into the room, and they start communicating with each device. There are methodologies to do that. One of those methodologies is called self-organizing networks. We'll discuss that in a few minutes, okay? And the other thing is cognitive radio. So as we mentioned, the frequency is already, or the band of the spectrum is already allocated to existing users. However, if you look at the utilization of that, you will find that it's not fully utilized. Sometimes I own the spectrum, but I'm not communicating. I don't want to communicate now. So if that's the case, can I increase the efficiency of spectrum usage by making that spectrum available to other users while I'm not using it? Yes, and the way to do that is called cognitive radio. We'll discuss that as well in a few slides, okay? Another thing is in terms of powering your devices rather than having to charge them. People are thinking also now about energy harvesting. So this device can collect energy from PV panels, from when you shake the device, it collects that kinetic energy and it charges the battery without really having to every time, okay, I need to charge my phone, oh, it's now discharged and I need to charge it again and so on, right? But that's again still an evolving. This is a very interesting technology. I will discuss it when we come to it. It's like a mode of communication that typically one would not think of as a way of communication. I'll come to it when we reach that point. I'll stop. So going back to what we're talking about, now we go back to revisiting the cellular. This is how a cellular system looks like. In each one of those hexagons, the center is typically a base station. You can see base stations outside there if you go to the street, either on top of buildings most of the time, like the one, for example, on top of the library, okay? Or you can see them actually with poles coming from ground all the way up, but that's the less common situation. It still happens, but it's less common, okay? Those are central units or central places where all the cell phones that are around the base station in this region, which is called the cellular coverage of a single base station, they are all connected to this one. And if you move, like you are riding your car or moving in the street, walking in the street, until you became further from this and closer to the other, you are transferred, so you start establishing your connectivity through the new base station, not the old one. And the way this happens is something called make before you break. So if your node is moving from here to here, so if your node is moving from this point, it's connected here. It goes to this point, it's still connected here. Now when it crosses the boundary, it's closer to the other one, right? In this case, it stays connected to this and establishes a new connection here. And then after that, it breaks this one. The reason is if you break first and connect the new one, you will have an intermittent or an interruption in your connectivity, right? So this handoff algorithm is, if you move across the boundary, you stay connected to this, and you start a new connection here. After this connection is completely successful and usable, you break the old one and you stay with the new one, right? So this way, you guarantee that you don't have any interruptions in your connectivity. Okay, that's called the handoff in cellular systems. One other important thing, we mentioned that the frequency is a scarce resource. We have very little availability in that resource, right? So you want to make sure that you don't waste the spectrum. Now, when you have two base stations that are adjacent to each other, so they have a common boundary between them, right? If you have a user standing at this point, if you have a user standing just at the boundary, and that user is trying to communicate with this one and that one at the same time, that make before break that we talked about, right? If both of these are using the same frequency, then the signal is gonna cause interference, right? Because you are now trying to communicate with two different signals, one with this base station, one with the other, but both of them are at the same frequency, so they will interfere with each other. Yes, I will take your question. So this one is gonna be some data going here to establish the connectivity, some other data going here. By the way, when I draw the arrow in actual wireless communication, it goes everywhere. It's not really directed to that base station, okay? So this means that whatever I'm trying to send here is gonna also be heard by this one. Imagine two people talking at the same time to the same person with the same level of power, right? Or the same level of voice. I will not hear anything. I will just say, please, I'm hearing noise right now. One of you has to stay silent so I can talk to the other, right? Or you want to establish two different frequency ranges so they don't interfere together, okay? So whenever there is a common boundary between two base stations, each one of them is going to be using a different frequency from the other one, right? But then we don't mandate all the different cells to use different frequencies, because if you know, like between this one and this one, there is no common boundary. So if they use the same frequency, if a user is here and talking to this one, this is not going to be able to hear it because it's far away, right? And similarly, if a user is here talking to this one, this will not be able to hear it because it is here, it's far away from this one, so the signal is going to be weak. So the same frequency used here, I can reuse it here and here. The same used in the green, I can use it here and here and so on. Your question? If it gets crowded in one place, there are two options, right? If the network designer is accounting for this, they create something called a small cell. If you go to downtown area, for example, many users there because they have lots of buildings and many tenants in these buildings, whether they are ministries or visitors to the city center or whatever, right? So many users. In that case, you start creating within, rather than covering this whole area with one base station, you use smaller base stations, right? And those smaller base stations have less coverage area. So instead of making this whole area covered by a single base station, you start adding more base stations here, and each one of them has a smaller coverage area. So now the amount of users within this region gets split across those different small cells. And not only that, also indoor versus outdoor coverage. The signal coming from outdoor becomes very weak indoor. So typically they install devices that looks very similar to the Wi-Fi, but they are actually Ooredoo devices that are cellular. And they call those Pico base stations. So very small or micro or Pico base stations. Okay? Did I answer the question?
Doctor, I have a question.
Yes.
Here, when you will make like a small base station, you will divide the frequencies more or what?
Yes, you will start doing more frequency division within the same area. So you start.
More power needed.
Depends, because again, the coverage of each one of them is small, so it depends how many and how you divide it and what's the typical channel characteristics. It might not be the case. It might be more or less the same power consumption. But definitely more challenge in terms of frequency allocation, because now you have to divide many frequencies within a smaller range, keeping in mind that you do not interfere with the next cell, right? So it becomes more challenging.
Different frequencies.
For those smaller cells, you apply the same rule between them again. Each one of them has a coverage area. No adjacent small cell should have the same frequency as the one next to it. So exactly as if you have zoomed in and you're only looking inside that cell to see those smaller pieces and apply the same rule.
How can we control the area?
Control in terms of what?
The area.
We don't control the area. We typically do the opposite. Typically what happens is they install them based on initial allocation, and then they tune the power based on measurements of that place. So they want, for example, this. It's never, by the way, it's never as ideal as you see it here. It's typically like, okay. So what I mean by it's never as ideal as you see it here is, if you go to an actual network, you will find probably for this access point, the coverage area looks like this. It's not really that hexagon, nice hexagon that we talk about, right? The whole idea is between this one and the next one, I do some measurements and power adjustment to know exactly where is the point that the power of this one for a receiver becomes higher than the power of this one for a receiver. And that's the boundary between the two. You got my idea? You got how it's done? Yeah, okay. And the end shape does not look as nice as this. This is just for demonstration. Okay. Any other questions?
Doctor, can you repeat again? Like, do we check when the power will get 3
Yeah.
zero?
So I'll tell you how the testing process happens, and then probably this will clarify what I mean. So you have here one axis, one base station. You have here one base station. Okay. You make sure that both of them are, for example, transmitting with the same power. So both of them are emitting out signal in all directions with the same power. Okay. Now, what do? You bring a measurement device and you start close to this one. Of course, you expect the power coming from this one to be higher than the power coming from this one, right? And then you start moving, measure, move, measure, until you reach a point, right, that you find approximately the power coming from here is equal to the power coming from here, right? That point is gonna be that boundary that says this is the end of this cell and the start of the new one, okay? Not necessarily gonna be in the middle between them. It depends on what's happening in the surrounding. And the surrounding is not empty. It has buildings, streets, trees, everything, right? So it's not necessarily that this is gonna be exactly the same distance from both, okay?
My point is that when the power reaches 0, but if it reaches 0, then
No.
you won't
It's
receive
just
it.
one becomes higher than the other. It does not reach, because otherwise you will not be able to do that, maintain the original one until connect the new
Yeah,
one and then
once you see.
disconnect, yeah, okay? Okay, so, yeah, so this is for the guys who are cellular phones. These guys are working on licensed bands. So they go to the CRA, for example, here in Qatar, and the CRA is authorized by the government to take fees from them. A lot of money, by the way. It's like hundreds of millions, okay? And in return for that, it says this frequency is only yours, no one else can use it. No one in the country here can use it other than the one who bought that frequency range, okay? On the other side, most of those devices that are owned by individuals, like the Wi-Fi and stuff like that, they work on another range of frequencies called the unlicensed band. These are certain ranges of frequencies, again, like organized and arranged by the CRA, but you don't pay fees for those ones. You only need to verify that your device is compliant with requirements of these bands so you can use them. So any Wi-Fi, for example, which is using here, probably using the 2.4 and the 5.1 gig, right? These are two unlicensed bands, but the device here is required not to transmit at any point in time more than 100 milliwatt. It cannot go higher than that. Otherwise, it's going to prevent other users in other places from using the spectrum. So they put a requirement, and the device comes certified either by the FCC or some certification that says that it is compliant with the unlicensed band, right? If it's not, they will not allow it to get into Qatar. That's why when you get a wireless device, typically they need to check it before you get it into the country, because they want to make sure that you are compliant with the requirements, whether you are not allowed to get it because it's using a band which is already licensed, so you cannot get it into the country because it's not supposed to use that band, or if it is in an unlicensed band, then it's compliant with the requirements of the unlicensed band. Okay? طيب, a quick recap, so, or a quick important note. It might look like that I'm telling stories and there is nothing to do. I don't want you to memorize anything, but I want you to figure out key ideas that we are discussing here. For example, different technologies might have different coverages. When we said satellite covers large areas, when we say cellular is smaller areas but more as opposed to, for example, Wi-Fi inside buildings and so on, right? Or when we say that what's the difference between licensed and unlicensed? If I have a device which is doing this or that, and it's owned by a particular entity, do you think that this should be using licensed or unlicensed, right? So try to get those ideas from what I'm saying, okay? Because the typical thing that runs over your head right now, what kind of questions I can be asked in this? So now I'm trying to tell you what kind of questions you can be asked, okay? Okay, we already discussed the frequency reuse, so I'm gonna skip this slide. Newer technologies are typically in cellular systems. The key factor that changes from one technology, LTE and 4G, like more or less came at the same time, to another technology is the increase of data rate. That's number one. And then other things, like for example, 5G was supposed to be, originally was supposed to be handling more frequency band, the millimeter wave, and in addition to, which means more types of users. And it was also supposed to handle something called ultra low latency communication. They call it actually ultra reliable low latency, URLL, okay? Which means that you can communicate with high speed of communication, with very minimum delay. The delay was limited to a certain fractions of milliseconds, right? And without really having this connection with low reliability. So it does not get disconnected quite often. It stays connected most of the time, if possible, all the time, okay? Achieving that was supposed to happen if certain technologies were developed on time. Did not happen. So now the URLL has been moved to 6G. It was not achieved actually in 5G. Similarly, the terahertz and the millimeter wave, most of it is going to be implemented in 6G. I'm not sure if the terahertz is going to be implemented. It might be another promise that's going to be broken when we go to the 6G. But the key idea always is when you move from one technology to the other in cellular, higher rate, higher rate, higher rate. So you go from 50 to 100 megabits per second to something like, currently we are talking about, in 5G, we are talking about gigabits per second, right? So it's no longer megabits per second. You should be very close to gigabits per second. And if you go to the 6G, it's expected to be terabits per second. Even millimeter wave will allow you close to the terabit. So if you use, when we saw that demo by Uridu, of course it was in a very nice, non-crowded area and everything was tuned to the perfect, but it shows 800 gigabits per second connectivity. So that's really a very high rate, right? Okay. One important thing also, all our, so those things that we'll talk about, the speeds, the ways, using MIMO, all of these are kind of physical layer connectivity or physical layer properties, but all our networks nowadays are using TCP/IP. So eventually at service level, at application level, at connection level, you are using TCP/IP. You have an IP address, whether this is your mobile or your iPad or your computer, and you are communicating using the IP packet format. Everything is using the TCP/IP, and there is no alternative technology nowadays for TCP/IP. It's one thing that carries with us. There is something called IP version 6, which is being currently implemented to allow more number of devices with bigger address ranges, but we are still TCP/IP in all, or UDP basically, and IP. But the key factor is we are using IP networks in all these devices. Okay, even when you communicate with satellites, it's still an IP network. Okay. Wi-Fi, key factor in Wi-Fi, in the recent advancement of Wi-Fi, is the ability to support multimedia. The problem with Wi-Fi, and there was a slide specifically about that called why Wi-Fi sucks. Okay, it doesn't really perform as required when it comes to multimedia. Multimedia means video, voice, in addition to the ability to transfer text and audio things, right? Now, the key factor is when you talk about voice or video, that the network is required to provide certain guarantees on delay. So the delay cannot change a lot, and certain guarantees on the data rate. If the data rate drops, your video is gonna be corrupted and you'll no longer be able to see the video, right? Those are called quality of service guarantees. Okay? Now the issue is Wi-Fi by nature, by its original design, is using something called contention-based approach to allow multiple devices to exist at the same time. What does this mean? We have all our phones here and they want at the same time to connect to the Wi-Fi of Qatar University. So they want to talk basically to this access point that you see there, right? And we are all in the same frequency range because this access point is working, for example, on channel 10, which means a certain frequency range. So how do we do that? And there is no coordination between us that says, okay, I will allow you to use your phone and switch off mine. And then after you finish, she's gonna switch on hers and start, and you switch off yours and so on, right? So how does it happen? It happens by a protocol called contention-based. In the case of Wi-Fi, it's called carrier sense multiple access, okay? With some extension, I will mention it when we go to that. The key idea here is, imagine that we have many people in this room and they all want to talk to a single person. What would happen? The first one who talks, the others are going to stay silent until he or she finishes, and then one of the remaining ones is gonna start talking. When the others hear that someone is talking, they are gonna stay silent until that person finishes, and so on, right? So what do? You typically listen before you talk. So you listen first. Is someone talking? No, then it's my chance, I'll go in. It can happen sometimes that two of us are very eager, so they listen, it's available, they start. It happens a lot, right? They start talking at the same time, but when they figure out that they have collided because they have talked at the same time, they will stop, and then randomly one of them is gonna start and the other one is gonna stay waiting until the other person finishes, and then she starts talking, right? That's called, in communication, that's called carrier sensing. This is the listening part, right? Multiple access, because it allows multiple devices to use the network at the same time, supposedly, but it's not exactly at the same time. They just have some kind of a protocol between them to make sure that they don't collide with each other, right? Now the issue with this is what? Now if I have a piece of video that I have to send within a certain time delay, because for example, it's a video conference, right? I cannot really keep my data for a long time. So how can I guarantee that I will have some access to the medium? I cannot. Might be that I listen, I find someone else is talking. I stay silent. Listen after maybe half a second, I find someone else is talking. So I stay silent. Listen one more time, and then my video has been delayed, and I cannot guarantee that it will be delivered on time, right? By nature, this was difficult using Wi-Fi, to use it for multimedia. And you will notice that a few years ago, we did not have really any wireless connectivity to project on a screen. But nowadays we have it, and all of these are using Wi-Fi actually, okay? Why? Because now there is part of the standard of Wi-Fi added to the access methodology that allows to reserve a particular time for a particular user who wants a certain quality of service guarantees, right? We will discuss this in more details when we talk about the Wi-Fi in next lectures, not today, okay? Standards of Wi-Fi are a lot. Why do we focus on Wi-Fi? Because of two things. It's a very prominent technology, and it's the one that we will use for your project to try to break into its security system. So that's why we focus on Wi-Fi. Yes? You have a question? No? Okay. These are some of the existing Wi-Fi. So B, like an old technology. A and G, they are still in use nowadays, but they are not the best in terms of their rates. And now we have the AC and the N. That's the most common Wi-Fis. They claim that they can reach something like 10 gigabits per second, but I haven't seen this yet. Probably I've seen Wi-Fi's doing 600 megabits per second, up to 1 giga, but I haven't really seen devices doing this kind of claim. But who knows, maybe. They typically have a range of up to 100 meters. After that, you lose the connectivity with your Wi-Fi, regardless of the technology being used. We have discussed this. So we have discussed this story of why Wi-Fi has an issue, right? And we talked about the carrier sense multiple access, right? But there is something called carrier sense multiple access with collision detection. This is used in wired connectivity, not in wireless. And if we are talking about Wi-Fi, which is wireless, it's called carrier sense multiple access collision avoidance. So instead of this, you have CA, so /CA, which stands for collision avoidance. What do we mean by the collision avoidance, or what happens? Simply the system is implementing that random weight in a systematic way. So I listen to the medium now to see if someone is talking or not. If nobody is talking, I'm gonna immediately start transmitting. Not really immediately, but I consider it immediately. I'll tell you later why it's not exactly immediately. Now, if someone is talking, what will I do? I will wait for a random time and then listen again. Why do we do that? Because suppose that I have something to send and you have something to send. Both of us, we listen to the medium. We find that someone is talking. Both of us wait for the same time, and then we'll try to transmit at the same time. That's a collision. So to avoid this, each one of us is gonna randomly select, because we cannot coordinate, because we cannot talk to each other anyways, right? So the only other option is to select a random, so you generate a random number on your side, I generate a random weight number on my side. The chances that we will generate the exact same random weight are very slim. Can still happen, but they are very low chances, which means that chances that we will collide together are reduced, right? Which means an increase of the efficiency of the network.
Doctor, practically here you're talking about like opening a browser or something, or about
Anything you want to send, opening a browser, sending a file, whatever requires you to connect to the network.
Same network.
Yeah, whenever you want to access Wi-Fi physically, when you want to access anything from the web using your Wi-Fi connectivity, physically your device is talking to this access point. It's yours and mine and everyone here, right? So whatever, receiving emails, sending something, opening a session to a web browser, in all these cases, my device is trying to communicate with this. And the same for your device and so on, okay? Self-organizing network, I mentioned to you the ad hoc. Now, how does this happen? The key high idea is when we have devices in the same place and they want to communicate together, they exchange some type of messages between themselves, right? Initially, there might be some collisions, but some successes as well, until they all recognize the capabilities of each other. And then, you know when you sit in a team and they tell you pick a leader, and you sit in that team and maybe everyone says, so a natural leader evolves, for example, so everyone says, Fulana, that person is our leader, okay? Similarly, but here it's more systematic because these are devices, not human beings. So they exchange information about their capabilities quickly with short messages, right? And once they do that, okay, they figure out that there is a device that has better capability than the others. They choose that as the hub, the central one, and everyone talks to that hub, and it controls now the network around it, right? Saying you have access now, and so on. So that's called self-organizing networks. Of course, there are many methods and many details inside that, but we cannot cover that in this quick lecture, okay? Satellite, two types of satellite systems. As I said, satellites, generally speaking, are characterized by larger coverage area, okay? But then they are characterized also by some disadvantage. A satellite, which is of type 1, called geostationary, that one is typically at altitude which is 36,000 to 39,000 kilometers above Earth. Okay? It's a very long distance. So whenever you want to communicate through satellites, you cannot really do anything about the propagation delay. Your signal travels with the speed of light. For that signal to reach from ground to the satellite is going to take more than a second. and for that signal to come back to you, it's going to take more than a second, and you cannot do anything about that. You cannot reduce it to milliseconds because you cannot travel faster than the speed of light, right? In order to resolve this, there are closer satellites called low Earth orbit, LEO satellites, okay, that are typically at between, they say 100 kilometer, but typically they are between 300 and 600 kilometer above Earth. That's a much shorter distance, and then you can communicate on a faster way. The delay now, the propagation delay becomes on the range of milliseconds, okay? Differences, the geostationary satellite is characterized by the fact that it rotates around the equator, and it rotates around Earth with the same speed that the Earth rotates around itself. So it stays always focused on the same region, right? All the time it's rotating with Earth with the same speed, okay? LEO satellites, you cannot do that. Lower orbits requires faster rotation. So because this is the case, and in order to do them in a way that covers most of the Earth, they do the orbit polar, so they orbit this way while the Earth is rotating this way, right? So now, when they rotate fast, it means that I rotate a couple of times before this rotates, and then a couple of times, and so on, right? So it means I can cover all the Earth with one, but at different times. And the same location is exposed to the satellite a few times per day. Sometimes in the morning, sometimes in the night time, okay? Now, if you want to use those that does not stay in front, that's another thing to think about questions, right? If you want to use LEO satellites to do something like establishing a communication system, you cannot, because this communication system is going to be connected with one satellite, it's going to be connected, and then when it goes to the other side, it's no longer connected. And then at some point, I'm rotating really away from the country, so nobody can be connected. That's not good for a communication system. It's nice for taking pictures of different locations of the Earth, for example. If you want to use them for communication, you have to use many of those satellites, such that at any point there is one rotating this way, one rotating this way, one rotating that way, and so on. So you can establish a coverage at any point in certain location. There are a couple of those satellites above that region, can carry the signal, communicate with the others, and then send to the destination. This is called a constellation of LEO satellites. Okay? Starlink is a good example of this. So that Elon Musk internet connectivity through LEO satellites is a constellation of a large number of satellites, not just one or two or three. Okay. GPS is another example, and it is a LEO satellite. GPS is the system used to tell you where is your location on Earth, right? The International Space Station is also orbiting at LEO orbit. So it's around 550 kilometers above Earth. Bluetooth, just quick information here. Data rates of Bluetooth is not the greatest, but it's not the slowest. Okay, so it's kind of on the slower end in terms of data rate. Frequency typically 2.4. This is an unlicensed band. But the nice thing about Bluetooth is that it's very efficient in terms of power consumption. That's the key advantage of Bluetooth. And it's always for short range communication. So you can see that the range of communication, is it mentioned here? Typically, 10 meters. Even this extendable to 100 meters is really an exceptional case. Typically, we are talking about 10 meters, so in the vicinity of the same room or just outside the room, okay? So they are nice replacement for any short cabling, but if you require higher data rate, you cannot use Bluetooth, and if you require more energy efficiency, Bluetooth is your choice. So they're good for energy efficiency. Zigbee, a little bit different, higher rates, slightly worse in terms of, lower rates, slightly better in terms of power consumption and range coverage, and they use also different frequency. Most of them, all of them are unlicensed. So these are unlicensed frequencies, okay? Now the emerging systems, I think I'll stop here and we can continue those next time. So next time we'll talk about some of those emerging technologies, and then we will move to more focus on security in wireless communication. That's what we'll do next time. As I mentioned last time, we are looking at wireless communication system and getting an overview on these systems for two purposes. Purpose number one is basically to give you an idea what kind of domain our wireless discussion is going to be, our security discussion is going to be, mainly focused on the wireless domain. So you need to understand a little bit about that domain from a technology and advancement perspective, as well as challenges. We will have a set of slides and lecture which is targeting the security challenges in wireless system, particularly focused on Wi-Fi. Why specifically Wi-Fi? Because of two reasons. It's a good example. And it's the one which is more prone to attacks as opposed to the infrastructure network using cellular phones. Cellular phones are generally more protected. It's more closed system. Wi-Fi tends to have like a degree of openness, and that makes it susceptible for attacks, threats, and accordingly requires more considerations when you are learning about security or when you are designing a secure network. The other purpose to pick Wi-Fi because it's directly related to the project that you will be given in this course. And today, in the last part of the lecture, I will give you a briefing about what's the project, and then we'll post the full description on Blackboard, and you'll start having your lab sessions next week, inshallah. Okay. Now that's one part. Why do we study about wireless system? Because this is the stage that we will use. And the other thing is the course is fundamentals of secure communication. So we don't really want to study security detached from the actual communication system. So again, part of this course is to educate you about communication systems, regardless of the security aspect. So that's why we are spending some time on these slides. And by the way, at the start of these slides, they are already on your Blackboard since the previous time. But at the start, it mentions that they are from a different book. So that you cannot find this in a chapter of the textbook. Okay. For the coming ones and the first one, the introduction one, it's mentioned at the start of each set of slides which chapter, and if not the full chapter, you will see the chapter name and then list of sections that are addressed in. That might help you if you want to refer to the book every now and then to kind of understand better or enrich your knowledge on the topic. Okay, so the first thing about emerging technology, we went quickly through the list last time, which was on the previous page, but let's now look in detail. So first thing is the continuous advancement of cellular network. So cellular network keeps on moving forward, right? We used to have GSM, 2G, 3G, 4G, 5G, and the next one is 6G and so on. So what's happening as we move from one to the other, providing more service capabilities, so it can serve different types of traffics with certain requirements on those traffics called the quality of service requirements. And the key factor also is always increasing in speed of communication. Okay. Now that increase in speed of communication, remember, we have three parameters in any communication system that you are kind of juggling together, right? Does anyone remember what were these three parameters? So the rate or the speed, and the error or the reliability of the network. So you want to reduce the error or increase the reliability. You want to increase the rate. And what was the third one? Power or energy. So mainly we talk about energy because it's power across longer time, okay? So the energy also, you want to reduce the consumption of the energy. However, when we move on those systems from 1G to 2G, 3G, and so on, we are always increasing the rate. And nobody wants to sacrifice the reliability. So what's happening actually is we are spending more energy. So we'll see also in the next slide that there is a trend also that says, hey, you have to hold on that with the advancement of the wireless network. So anyways, with cellular networks, in order to provide more reuse and more number of users, to allow more number of users, given the fact, remember that on these cellular networks, right, between one cell and the other, we are using a different frequency, especially adjacent cells, right? And then we reuse the frequency as we go away. So here, all these have to be different frequencies because they have adjacency to each other, right? But if you take this one, it can use the same frequency which is used in this one because they are not adjacent to each other. We call that concept frequency reuse, right? And we have addressed it already in the previous lecture. With the advancement now, more techniques that allows extra number of users on the same frequency, same time, same cell. One of these techniques is what's called beamforming, which is the ability actually to point the signal towards the user only. So your signal is going to, like, if we want to see how this is going to work, so assume that here is your user. Let's say it's a cell phone, right? And here is your base station, and that's the kind of the antenna above the base station, okay? And you have another user who's in a different, slightly different location. So now both of these, they belong to the same cell. So both of them are in the same cell, right? They are not in two different cells, okay? Now, if you want these users to use the same frequency and they communicate at the same time and whatever, okay? So the only possibility now is to make sure that your signal coming from this is focused only in the direction of this guy. So this does not see it at all. The other one here does not see this signal at all. And you can also formulate another signal with the data intended to the other user, right? This is called beamforming. And in order to be able to perform multi-beamforming, we use a technology called massive MIMO. Massive MIMO. So MIMO means we are using multi-input, multi-output, means that we are using multiple antennas for transmission and reception. Massive MIMO means that we are using a lot of these multiple antennas. So current technology of massive MIMO is talking about 64 by 64 antennas. So the total number of antennas is 64 times 64. This is the total number of antennas inside that. That's a huge number of antennas. And now you can pick a few of them and use them to form a beam in one direction, few other antennas and form a beam in another direction, and so on. This is called spatial multiplexing. So we use space, the fact that the two different users exist in two different spaces, and then we point a signal to that one and a signal, both signals with the same frequency. They communicate at the same time, but they don't see each other because the beam, the energy is focused only in the direction of the intended user, okay? Generally speaking, to get a narrower beam focus, you need more elements of antenna. And of course, to get multiple beams, you still need more elements of the antenna. So that's why we need to opt for a large number of antennas if we want to do both. Pointing in a certain direction, not a very wide beam, because a very wide beam would not be useful in this case. If your beam was something like this, it's gonna interfere, right? Because it's heard, it can be sensed or heard by both users. So if you are using two beams and they look like this, then this guy is gonna have interference. Maybe this guy no, luckily. But again, you cannot really focus the signal unless you use larger number of antennas, and to have multiple of those, you need even larger numbers. The next step is gonna be 256. It's now being tested in labs by 256. That's even a much larger number of antennas, okay? Again, the drawback of massive MIMO is the complexity of this system. You can imagine that this is a very costly system. Sorry? And energy is another factor, but has nothing to do with this. It has to do with the fact that those beams require higher rates, so the rate is the more dominant factor in this case, okay? So that's one technology, the usage of MIMO and massive MIMO for spatial multiplexing, right? And generally speaking, also, you can use something called relays, okay? So you can, for example, instead, if you want to reach a particular user, like this one, for example, and for some reason, the base station here is occupied by other users. So sometimes they do what? They send the signal to one user, and that user carries the signal to the other one. So they can do relaying across different users of the network, or relaying across base stations, right? So I want, for example, I have a user here who's not really able to communicate with this base station because it's over-occupied, right? So that user might be connected through another user and then to a base station, and then that base station is gonna take that user to the backbone of the network, right? So that's another option which is being tested for newer technologies called relaying or multi-hop relaying, okay? The other thing, as I mentioned, with those increasing rates, and as you commented as well, above, okay, with those increasing number of rates of transmission, then we need to spend more energy. And now it's becoming a big issue because cellular systems are becoming like big consumers of energy. They are now comparable to high energy demanding factories like cement factories. And so the cellular system is becoming actually an issue in terms of consuming energy. What's the problem of consuming energy? Environmental mainly. And then cost-wise for carriers, because they pay for that energy. It does not come to them for free. Ooredoo pays for the electricity that they use, and Vodafone does the same, and every carrier does that, right? The main driver is actually the environment. So nowadays there are researches and actually even some techniques applied where they try to save energy consumption in the cellular system. I can give you an example, right? Again, they cannot sacrifice the rate because that's a requirement of the users. But for example, any of those base stations, even if there is no user connected to it, the base station needs to advertise itself. So it needs to stay communicating wireless signal so that whenever a user comes in the range, that user can be associated to the base station, okay? Which means that it's running all the time, even if there is no user connected to it. There are now, and we even have been in some projects in that domain with some of the carriers here in Qatar. There are now carriers that are looking at something like, okay, if I know that a particular base station is in a remote area and I have statistics that tells me that, for example, there are very slim chances that this base station is going to be used over the night. It's only used during the morning, right? Then I can simply go and switch off the transmission of that one. The advantage is I'm saving energy. The disadvantage is if a user comes into this, that user will be for a while until the base station is brought up one way or the other. That user is going to experience outage because they cannot connect to the network. They will not find any dashes or signals that says that they are connected to the network. Of course, this is something very risky for a carrier to do. So that's why they need to rely on complicated methods to figure out what is the ideal or the optimum time that they can pick to actually switch off, and then before the end of that time, they switch it on even if there are no users, to be ready for the next coming user, okay? So researches in that domain, that's just one example of the methodologies. There are many other methodologies and researches in that domain are very active. It's called green communication, okay? And green comes from the fact that it is more environmental friendly, right? Everything which is environmental friendly is called green. Any questions? الساعة 2 ليها تأثير أنا عارف. Okay. Another technology, we also gave a glimpse on this last time, but we are going to discuss it a little bit in more details, which is called the ad hoc network. Ad hoc network means that you have a group of users, group of wireless users. Let me, before doing that, what's the opposite? The opposite is infrastructure network, which is a network designed ahead of time. An example of that is Wi-Fi. So Wi-Fi, you have access points in certain locations, and it's well known that if a user appears into this system, that user is going to connect to the access point, and then the access point is going to carry whatever traffic to the next user or next access point to the backbone of the internet and so on, right? So that's pre-designed, it's well known. Same thing for cellular system. There are cells covering different areas. You design your network this way. Whenever a user comes into the picture, users don't talk directly to each other. They have to talk back to an access point, a base station in that case, and then it carries their information to the next user or to the backbone of the network and so on, right? If this is not the case, we are, for example, riding a couple of boats and sailing into the Gulf, and we go outside the region of coverage of the cellular system, right? And we have two boats that are probably maybe 1 kilometer away from each other or 500 meters away from each other. Each one of those boats has a group of people and they have their cell phones, but they are not connected to the backbone of the network because there is no coverage. Still, people on those two boats want to communicate to each other. The one way to do this is using their cell phones, is to allow the technology on the cell phones to, for example, use Wi-Fi or Bluetooth. Bluetooth is not going to reach 1 kilometer, but Wi-Fi might reach that with certain enhancements to it, right? So they use the Wi-Fi module on each one of those phones, and they establish a network. There's no access point in that case. It's not a Wi-Fi through an access point. It's just from one cell to the other. So the connection becomes as you see it here, right? Everyone is capable of talking to another one, which is a peer. None of those is different from the other, right? It doesn't have to be a full, we call this a mesh network, and it doesn't have to be a full mesh. Full mesh means everyone has a direct connection to everyone else. This is not the case. we can see that these guys, for example, they have direct connection, but there is no direct connection between those. However, they can reach each other through a third point, right? So if I want to communicate to this guy, I'm gonna send my message to the neighbors, and then they see the address, they say, okay, this is not for me, it's maybe to my next neighbor, they send it to the next neighbor. If that's the intended one, it stays there. If not, then hop to the next neighbor, and so on until it reaches the person that I want to talk to, okay? This whole setup happens by exchanging messages between the phones or the devices, right? For cell phones now, they do not allow this by default. You have to install some application on your cell phone that uses either the Bluetooth or the Wi-Fi to establish something like this. And if you want to go and read in the news about something related to this, I don't know if you remember, there was some students rising in Hong Kong a few years ago, objecting to the government of China and the rules that they want to impose on the I don't know whether you call Hong Kong a country or a region or whatever. Sometimes it looks like belonging to China, sometimes not. But anyways, they were objecting to some government rules, and the typical government action that we saw in similar situations was they cut the cell phones, so they could not communicate to each other. But those are top guys in technology, so they created an app which is a peer-to-peer, and then they managed actually to establish connectivity among themselves without the need for the backbone. So the phones were talking to each other in a similar fashion and using every other phone to kind of relay to a further point. So even if Wi-Fi covers 100 meters, then you can reach 1 kilometer by going to one, next, up to 10, for example, which is gonna give you a coverage of 1 kilometer and so on, okay? But as I said, this is not by default. In the case of cell phones, you need apps to establish something similar to this, okay? The link between them is Wi-Fi physical channel. So I have a Wi-Fi module on my phone. You have a Wi-Fi module on your phone. That software is using the Wi-Fi to communicate to the other one, right? And Wi-Fi itself has a mode of support which is not based on access point. It's called ad hoc Wi-Fi. Yeah, standalone. But that standalone module, currently the default usage of that is one of us has to be the host of the other. So one of the cell phones becomes the host as if it is an access point, and the other one as if it is a terminal, right? This is what you do, for example, when you do hotspot through your phone to your iPad or other devices or your computer or whatever. So what's happening actually is your cell phone is connected somehow to the backbone. It's actually connected to the 5G or 4G, right? And then through Wi-Fi or Bluetooth, it's connected as if it is an access point, as if it is a Wi-Fi access point connected to your computer and then taking your traffic to the backbone, right? But that's only one-to-one. If you want to do something like mesh that I'm talking about here, you have to install some specialized app for that. It doesn't happen by default, okay?
But we have the module itself, right?
You have the hardware, which is the Wi-Fi or the Bluetooth, right? That allows you to communicate with a certain physical layer property, right? But it does not create, this is kind of logical connection. So these guys, they know now about each other and that they exist in the same network, right? This is upper, higher level. It's not just physical. Physical talks about this guy sending some wireless wave and this guy being able to see it and vice versa. But what's inside and how do I know that this is a node with a particular address and this is a node with a particular address and so on, this is upper layers, okay?
Doctor?
Yes?
Doctor, what's the difference between Wi-Fi and when we say 5G or 4G? I know that Wi-Fi it's only for a particular coverage or a particular area. But when we talk about 4G and 5G, they are portable or you can move with them. Okay. So what's the difference? Is it the power that...
Many things. So these are two different modes of operation, but actually two different network types, okay? So the 5G, 4G, 3G, whatever, is a cellular network. So your main access here is one of those infrastructure access points in the outside, right? With typically with few antennas above, right? Typically there are 3 sector antennas above each base station, right? And the module inside here is a cellular module that requires a SIM card to be inserted to it. Or now we have eSIM, electronic SIM. And there is, in addition to that, they use certain frequencies identified by the carrier and the device. So they use, for example, 950 megahertz and 1.6 gig and 2.1, 1.9 gig, up to, there are frequencies up to 6 gig in the classical, okay? Different frequency ranges that are allocated to those carriers, to those phone providers, cellular phone service provider. And the format of the electromagnetic signal that they send is different. So they use modulation, which is different. They use data formatting. When we talk later on about the different layers and so on, they use a packet that has a format different from the Wi-Fi. Wi-Fi is a completely different network, which is composed of those access points, like this guy, right? And then Wi-Fi modules that are either on your phone or on your laptop or on your iPad, whatever, right? Each one of those has a piece of hardware inside that works with access point like this, does not work with base station at all, because it uses a completely different frequency. Wi-Fi is, what are the frequencies? 2.4 gig, right? And 900 meg. And the higher one is 5.1 gig. These are the possible frequencies for Wi-Fi. So different frequency ranges. Data being sent on the medium have different modulation techniques, different format, and the types of the devices are different. And of course, the limitation on the power is different. So this one cannot, because it's using unlicensed band, so it cannot really send a signal greater than 100 milliwatt. That's it. For the cellular, no, you can actually, either from the phone. Base stations are typically sending signals in the range of kilowatts. So base stations need to send because they have a large coverage area, right? Cell phones are different. The cell phone itself will not be able to send kilowatts because of its size, its battery, and it can kill the person, right? If I send the kilowatts from the cell phone, I'm gonna die myself. It's gonna fry me, right? So it has to be again lower. But again, the fact that the base station can send higher power means that you can design the cell phone receiver in a simpler way. The fact that the cell phone sends very limited power means that you need to complicate the design of the base station to be able to receive that. And this is why the base station is much larger than the device, the phone that you carry, okay? But again, these are two separate networks. The only thing that connects them together is that through both, you can go to the internet, right? Whether through 5G or through Wi-Fi, you can eventually reach a website or a server for FTP or a place to put your files like Dropbox or Google Drive or anything like that, okay? But in terms of physically, they are completely different, okay?
So Doctor, we can say that those modules, they are the source, and they generate those.
Which modules?
I mean, for Wi-Fi.
Yes.
They are the source. They are not connected to any base station, whether it's.
No. The only relation I mentioned now is that through both you can get to the internet. And then, if you remember actually it was last lecture, I mentioned that the trend right now is that you have a single device with multiple technologies, right?
Yes.
So these are two different technologies. Each one of them has its own physical characteristic and its own ability and its own devices and everything. Only thing that happened is on your phone, there is part or a module, which is Wi-Fi hardware. There is another part completely separate from it, which is the 5G or 4G or the cellular hardware, right? But they were able to put both of those on the same board inside the same cell phone, okay? That's the only thing. And then the cell phone can use this or that, okay? So it tries to give you some kind of, what we mentioned earlier, seamless connectivity. So you don't care, when you go into the building, if it finds a previously defined Wi-Fi, it will connect to that Wi-Fi. You go outside the building, so because Wi-Fi is typically cheaper to carry your data through, and then if you go outside the building and it can no longer find the Wi-Fi, it will use the existing 5G connectivity to carry your data, right? So the phone is only deciding whether, through a software, to carry the data on this or that. So for you, don't feel the difference, okay? But on a technology and module and hardware and software and everything, they're completely two separate technologies, okay?
Doctor, the broadband, for example, the one we have here in classes or even at home to provide Wi-Fi, they are not connected to base stations?
No, These ones are connected through the backbone to the cable that brings the internet connectivity to the university, which is probably connected to a switch through fiber to Ooredoo central unit, and then that central unit is connected through a fiber cable underneath the sea to Europe somewhere, right? And so on, right? But no, they are not, these guys are not carried through the 5G, okay? It's gonna be very expensive if they do that, and also limiting, because fiber so far can provide faster speeds than wireless. Okay, you're welcome. Okay, so in this case, we are talking about peer-to-peer communication. As I said, all these devices, they look the same, but in the case of infrastructure, there is kind of a server side, or they call it a master and a slave side. The small device that connects to the Wi-Fi access point is the slave, and that's the master that controls the traffic. However, even in these ones, there is something called self-organizing networks. So once you establish this connectivity, the devices starts checking with each other, and if they find one of them which is with better capabilities, like higher memory, higher processing power, higher speed in terms of the communication, there is a combination that defines which one has the higher capability, then they designate that as the master or the central unit, and everyone talks to that, and it becomes, that unit becomes responsible of distributing the traffic to everyone. So autonomously, they established something similar to the infrastructure network. That's called self-organizing network, okay? And we have touched upon that also quickly last time. A few terminologies to know about networks in general. The topology means the arrangements of the nodes and the connectivities between them with respect to each other, right? So for example, we call this type of connectivity that goes always through a central unit, we call this the star topology. This type, where everyone can talk to everyone, we call this the mesh topology, okay? There's another topology, for example, where you have only one cable, and that's a bit old technology, and everyone is connected to that cable, right? So this is called a bus topology. It's only one cable, and everyone reads and writes the information to that cable, okay? Some of the challenges in ad hoc networks, some of these are already solved, even though they're mentioned here as challenges because they came from an older book, and some of them are still big challenges. So for example, capacity region means the theoretical limit on the highest rate that you can reach on this network. So if you form this kind of network, what's the highest amount of data rate that you can carry across that network? This is called the capacity of the network, okay? Until now, there are no mathematical tools that's able to solve this problem, to find the maximum possible, I mean, find it theoretically, drive it mathematically, the maximum possible capacity or rate on such networks is not attainable. You cannot calculate that mathematically. You can do some simulations that gives you some approximation, okay? Resource allocation means who gets to talk when, who gets higher frequency, who gets lower frequency, who gets more bandwidth, who gets less bandwidth, who has priority over the other, and so on. This has been extensively studied, and there are lots of algorithms and options that you can choose from to do the resource allocation in such networks. And similarly, routing means, as I mentioned, if this guy wants to talk to this in a dumb network, it would send to everyone, and then everyone, if it's not mine, I would send it to everyone next to me. But this means that the network resources are duplicate in use, right? I put the same data occupying all the links in the network. That's not efficient. If there is a routing algorithm, then I know that the best way to talk to this guy, for example, is through this path from the beginning, right? So whenever I want to send information from here to here, I will only send it to this, and this will know that it has to send it to this, and this will know that it has to send it to this, and then to this, and then to this, instead of sending it to everyone, okay? This operation and figuring out the best path and storing that and accordingly deciding when to send the data to whom until it reaches its final destination is called the routing algorithm or the routing protocol. Again, this has been extensively studied, and there are many solutions. So it's no longer a challenge in these networks, okay?
How they know?
Again, whenever they establish the connection together, they start pinging each other with short messages, so I know exactly everyone is where and how many hops or units of time it took me to get a message from that particular user and through who, right? And after exchanging those, it's called the routing protocol, like the IGMP. It exists in the IP network, right? After that, everyone has some kind of a picture of the network, how to reach any other node, through which next node, okay? And after this settles, whenever they have something and they know that this is targeted to this particular IP address, for example, then the next one is the lower node, not the upper node. I send it to the lower, and then the lower will take care of it to the next hop, and so on. Okay.
And the messages that they are sending are IP addresses? Or?
It's called IGMP messages, and they're very short. They includes the IP address of the source, the destination, and some time counter that says it has been through how many nodes and how long it took for it to reach this point. Okay. And based on that, each one is going to build something called the routing table. Routing table tells me, as a node, if I want to send something to X, what's my next hop that will take it through the best path? And each one will have such a table in its own memory. Okay. Okay. Well, again, routing is a big topic. It's kind of like maybe 3 lectures at least in an introductory course in networks. Okay, so you probably need to. It can be extensively studied, but not in this course. But anyways, I hope I gave you at least an initial idea how it works, okay? The other problem, or the other, technology that tries to solve again the problem of scarcity, I don't know, it's getting a bit warm, huh? So it's okay, well, yeah. So the other thing that is the other technology also, or evolving technology that tries to solve the problem of spectrum scarcity is called cognitive radio. Cognitive radio means that you are trying, okay, let's talk first what happens to spectrum. So spectrum is divided into 2 parts. There is licensed and there is unlicensed, right? Unlicensed are a few gaps in the spectrum, like the examples now is 905, 2.4, 435 mega, giga, and 5.1 gig as well. These are unlicensed bands, so a few. And they are, if you want to use them, you don't need to go and get permission or pay fees for that, but you need to make sure that your device is compliant with certain restrictions. So in order for a device to operate in that band, they have to be certified. And typically, FCC issues these certifications, but there are others. There is the European Commission as well. And most of our local regulatories like the CRA here or the NTRA in Egypt or in most of the region here, they just require that certification to have been done somewhere, and then they allow the device to work, okay? Most of the time there are no local certifications because we don't have that many device producers. They mostly come from outside, right? Now, if your device does not have that certification, you are not allowed to import it into the country in the first place. As long as it works in one of those unlicensed bands and it doesn't have the certification, it's going to be prevented by customs. So they're not going to allow you to bring that device into the country, okay? So that they avoid any, in this case, it's going to be like, it's not going to be illegal use of the spectrum because the spectrum is not licensed, but it's going to be kind of an ill use of the spectrum. So you are using it legally, but you are causing harm to everyone else who's sharing the spectrum with you because it's not owned by anyone. So you have to make sure that, for example, when I talked about the Wi-Fi, they use unlicensed band and they are restricted, either Wi-Fi or anything that uses that unlicensed band, that the total radiated power from the device cannot exceed 100 milliwatt. Okay? Whether it's a device on your laptop or mobile device, or it's the access point. They cannot exceed that, okay? They also have some restrictions on the frequency roll-off, like drop of the frequency and so on, okay? Or the other option are licensed. And in that case, they don't have that much restrictions on the properties of the signal. Of course, you cannot go outside the band that's allocated to you, and you have to pay money for it. And when you pay money, you own that spectrum, okay? So you actually now have an ownership. So Ooredoo or Vodafone, they own their own spectrum. They have paid millions for that to the government of Qatar so that they can operate in this particular spectrum for their cell phone, okay? Now the issue is, okay, they paid for it, but what was found several years ago, this cognitive thing has started probably 20 years ago. So it's not really something happened last 2-3 years, okay? It was found that statistically, the example that I gave earlier, right? You have a base station somewhere. Okay, so base station, we put it as hex, okay? And that base station has only one user, right? And it has a band, I mean, again, by the way, inside the coverage of a base station, typically each user is either, so you have multiple users, they are either given alternating time slots, so this one communicates on this, but it's very quick switching, so you don't feel it, you feel as if you always have connectivity, or they are given different frequencies, so this user and this user within the total band, so this is a band in frequency. First part here is for user one. So if we say that this whole thing starts, for example, from 950 until 960, that's just an example, a trivial example. So from 950 to 951 is given to user one. And then from 951 to 952 is given to user two, and so on. So there is a split of the frequency across the different users. Okay, now this cell, for example, has maybe 30 available frequencies, which means that it can serve up to 30 users simultaneously without any other techniques, just using frequency multiplexing, okay? But at any point in time, there is only one user which is using this, and the other ones, they are idle because there are no users around the cell, right? But still I own the spectrum, so nobody else can touch it. That's a waste of resource, right? If I can find two things together, if I can find someone who can use this spectrum but benefits me because I paid for it and use it without affecting my service, I will explain what does this mean, then it might be a good idea to share the spectrum with those people, right? Or those technologies, okay? Now the first one, I need to benefit, which means that those that are allowed to use the spectrum have to agree with me, have to take my permission and probably pay me some fees. The second one is a bit tricky, and this is where most of the research is, okay? So the second one means two things. Those who are gonna use the spectrum, again, it should not be with any effort from my side. I own it, I want my service to continue correctly, and I get paid from these guys, and it's their responsibility to figure out a way to use the spectrum without affecting me. So they have to be able to do two things. The first one is they have to be able to avoid sending anything if someone who owns the spectrum is using it. So they need to use something like what we described for the Wi-Fi, listen before talk. You need to first, as a node, we call that a secondary node, okay? As a secondary node, you need to first sense the medium and see if someone is using now that frequency, I would stop, I will not do anything, okay? If it's not being used, I can go ahead and start using it, but for how long? That's the question. Because now if I'm using it, and all of a sudden, a mobile phone comes into this cell, that mobile phone needs to communicate immediately, right? It's gonna take me a while when that mobile comes in, until that mobile sends a signal. I can feel that there is another signal, then I will take myself outside. This means that I have caused a slight outage for this device. That's not acceptable by the spectrum owner, right? Because they don't want their service to be affected at all. So what to do? This is where most of the research is. Those two topics together. Number one, how to sense the medium and do not make mistakes, because sometimes you can make mistakes. You can think that there's no one, while there is someone, but their signal was weaker when it came to me, right? So that's one issue of research. And the other issue of research, how do I get out of the spectrum before affecting the other? One example that they do is they enforce those secondary users, the secondary users, let's put them as a triangle. They enforce them to have very low power level. So that when those guys come and they communicate, they can establish the connection, and the effect of this is gonna be as if the medium is slightly noisy. It's not really completely blocked by a high power signal, it's a very low power signal, right? So when someone from the actual owners, the primary users, the one who owns the spectrum, comes in and they want to communicate, they send their signal. The signal is much higher in power, so they can immediately establish the connection, and I will get out. So what I caused them is going to be very similar to that the channel was weaker, there was some kind of random change in the signal value or whatever, which is something always acceptable in any communication system. That's just one technique, and there is lots of.
What is the benefit? Because the system be used.
I can use a spectrum for a very low cost. I don't need to buy it. I just need to pay some fees.
Too low power.
Again, too low power means probably restrictions in my communication, but these restrictions might be okay for me if I want to send low data rate. I'm not really someone who needs to send very high data rate, or if I don't want to cover very large distance, right? So the communication between the secondary user, between one and the other, is always assumed to be within a short range because that's the need of that technology, whatever it is, okay? So it depends, right? There are restrictions on the secondary user, but you are providing them as well with opportunity, and they will use that if they think that it fulfills what they want to do, okay?
Okay, do you have the second user have to get back to the CRA also to get the approval, or it's only for
That's another issue. So who's involved in the ability of a secondary user to use the spectrum? That's another issue under study as well from policymakers. Is it that they just need to talk to the spectrum owner, or do they need to talk to? Most probably the regulator is going to be involved because they still need to certify their devices. They still need to tell the primary owner that these devices are going to perform what they are expected to perform, whether it's low power or sensing with high accuracy or whatever. So I think again, these things are still, cognitive radio is a topic that keeps on, it never made it yet to industry, but it keeps on being studied, and a potential for the next generation, and then a potential for next. The military guys are the ones who are pushing this all the time. Because that's radio with intelligence, so when you go to battlefield, it might not be, the desire in that case might not be that you are really trying to like share the spectrum with the primary user. It might be that you want to use the same spectrum of the enemy when they are not using it, or you want to jam the spectrum of the enemy when they are using it. So you want to know their behavior, when they are communicating, when they are not. The same applies, right? The same sensing and prediction and all these techniques, they apply for a different purpose. So the military guys are always pushing this cognitive radio into research all the time for the last 20 years, okay?
So it's not applied yet, right?
Not applied in actual running networks yet. With very little things, those guys, but with really, I mean, it's cognitive, but that's like the kind of the lowest level of cognitive. Typically, an access point has multiple channels that it can work on. So Wi-Fi, within the range of frequency allowed for it, for example, the 2.4, for example, is typically from 2.4 to 2.45 gig, okay? And within that range of 0.05 giga, which is what, 50 mega, approximately, yeah. So within that range of 50 megahertz, right, there are multiple channels. In older technologies, I think there used to be 11 non-overlapping channels. Later, they became actually more number of overlapping channels, okay? But anyways, so they use one channel. The access point sets itself, for example, to be operating on channel 7. And whenever you look at your Wi-Fi module and you look extra into the properties, you can see which channel it's using to communicate with this guy, which is the same that this guy picks. So it's controlled by the access point itself. I am always using channel 7, so anyone who wants to connect to this are going to be using channel 7, okay? Now, why would this one pick channel 7? And maybe you come a few days later, you find it on channel 10. Because it feels that there is no other radio signal other than the users themselves, but there is no other access point that's using this channel in, so it has a sensor, an RF sensor that tries to see which channels are being used now in my surrounding and which are not, okay? And at some point, if you bring another Wi-Fi point and you put it close to this one, and you force that other one not to act intelligently, and you force it to be in channel 10, after a few minutes, this one is going to switch from channel 10 to another channel. So that's some kind of cognitive to avoid interference, right? But it's not as intelligent as those complicated scenarios that are intended for the actual application of cognitive radio. So yes, a very reduced version of the technology is being used here and there, but not fully applied anywhere yet. Okay? Military guys, I don't know what they are doing. They might be applying it, but not saying it. I don't know.
And how can I check the channel?
How can you check if someone is on the channel, you mean? If it's being used, or what do you mean?
I mean the channel that is used for my phone.
Yeah. So how? Go to the Wi-Fi module and look for the like there's an eye, so you can click on that if it's connected to this one, and look for the information, and inside the information you will find some physical layer properties. Okay. We did not take a break today, right? Okay. Well, how about we finish early rather than taking a break? Okay. So I have only a couple of slides that are important. A little bit more, maybe 3. I will go through them quickly. They don't need that much details, and then 2 minutes talk about the project, and then I let you go. Okay, so we will finish early. Okay, so wireless sensor networks. Why this is a specific? I mean, these are again just wireless network, but they have a certain property or set of properties that are related to the application itself that makes them a separate domain. These are nodes that are equipped with some physical property sensors. Like, for example, you can think of those guys as air quality sensors. So they sense some gases in the air, right? And you want to cover, for example, the area of metropolitan Doha. So you scatter a few of those sensors around, but they have to stay connected together to coordinate, and also they have to be connected to a central point, which is collecting this information and processing it, right? Or it can be monitoring the health of a structure, so no vibrations, no breaks, no twists, whatever, in a building or in a bridge or whatever. Or they can be sensing something underwater, or they can be sensing RF radiation, whatever. The general idea is they need to stay well connected, because you want always to be able to access that data, right? They are typically remote, nobody's around them, which means from a security point of view, they are at higher threat, because anyone can come actually physically and play with the node and do something to it to interfere with your network, right? So you need actually to think more about their security. But on the other side, the nice part of this is that they don't need to send very high data rates. Typically, sensing is associated with small amounts of information. Like gases, probably you have what? 100 types of different gases, right? And each one of them, you need to just send a number that says, for this gas, this is the concentration. Overall, you probably need to send tens of bits every few minutes, because gases are not gonna change like every millisecond, right? They take a while, these physical phenomena, they take a while until a measurable change happens to them. So they are always associated with lower data rates, but on the other side, you want them to have very high availability, so they stay connected nicely, and you want them to be very energy efficient. Because of the fact that they are remote, you cannot really connect them to actual electricity. There are no outlets around them. One of them is, for example, thrown in the desert. So it has to be either battery operated or harvesting energy from the sun or something like PV panel or whatever, okay? And in all these cases, they have to consume very little energy, otherwise they will not survive. Or you have to go and change the battery every 2 days. That's not practical, okay? So these are the considerations for wireless sensor networks. They have many applications now spread all over the place. We have many of them. There is a particular technology for those guys called LoRa, so keep that in mind, L-O-R-A. It's low rate and longer distance communication protocol, okay? So it allows for communication over kilometers with very low rate and low power, okay? LoRa is also famous for doing some cryptocurrency mining as well. You can look it up if you haven't seen it before. You can subscribe to that and maybe gain some money at some point. Anyways, category of energy constrained radios in general, not just wireless sensor networks. These are, for example, your cell phone is battery operated. So this means that you want it to live as much as possible because it's a mobile device and you don't want always to be connected to the charger, like what happened here. Okay. You want really the battery to live much longer, so you don't have to do this charging quite often. And in that case, you need to design your communication system and algorithms to account for that. So the idea of energy constraint is another important idea. For those energy constrained, it's not only the battery and the charging, but you can also use some energy harvesting like PV panels. What is the difference between devices that relies on renewable energy sources like wind or sun or whatever, as opposed to the ones that you can actually connect them to the main electricity network? Availability of energy. The availability of energy for those that are connected to the mains is that it's always available with the same level, right? But when you talk about PV panels, right, It depends. I mean, the morning there is, in the afternoon or in the evening there isn't. But also during the morning, if it becomes cloudy, you get less energy. If you have a sandstorm, you will get less energy. If you rely on wind, the wind on one day is very quick, on another, or very strong, on another day is very weak. So the energy in general becomes fluctuating. This means that you don't have constant availability, and accordingly you need to design your communication to account for that. I don't always have energy to communicate. So when should I communicate and when shouldn't I? That's from one side, and the other side is the needs from the communication. And to match those, that's another area of research, okay? Last but not least, and I told you that this is quite exciting, is something called chemical communication. Okay? Chemical communication is something that happens in nature. Okay, subhanallah. The example for this is inside your body or inside our bodies, we have the nerve cells, right? Do you know how the nerve cells carries a signal from the brain to your hand or your finger to move as you desire? How does it do that?
Potential difference.
And hormones.
No.
Electronics.
هي في electric signal, but the electric signal is not the only carrier for this. There is also a release of chemicals between one neuron and the next one, right? So this, typically the neuron has like some kind of a head with some branches like this, and then a very long tail, right? And then at the end of the long tail, you have something like this connected to one of the sensors of another neuron, right? And then the long tail and so on. And then maybe for this one also, you have, it's connected to another neuron. And then you have that neural network, right? So it's not just electric pulses, there are chemical releases between one and the other. And the way these chemical releases are communicating is by encoding the information into the amount and the pattern. So if I send you a couple of molecules of that particular substance, which is typically proteins, everything here inside the body is dealing with proteins. Enzymes are basically proteins, right? And with that pattern, so two and then a pause and then one more. This means something. And if I send you 5 of them in sequence, this means something else. And if I send you a different substance, it means that you will issue a different response. And then the whole body is trained on this. If I get this particular chemicals into that location, for example, the muscle coming from the nerve, then the signal means that the muscle is going to react to that by contracting. And this is when you move your hand up or you move your arm up. And the same when you move it down and so on. Of course, lots of coordination. Where does this coordination happen? Through the learning process that you take from being created inside the womb until you reach the point where you can control your motor actions. 2 years, 3 years, you can control some, 2 years, 3 years old, you can control some motor actions. You become older, you can control more motor actions. You become older, you can actually do very complicated things like playing piano or do so very, very complicated coordinated motor actions, right? This happens through training. But the key idea here is signals are communicated through chemical material, right? That's called chemical communication. What's the application of this? Many applications. Nowadays, there is a branch that studies this. It's called multi-scale communication. The reason that they, and it's also called molecular communication. So rather than calling it chemical, and the reason they call it multi-scale because it can happen at the scale of microscopic or something greater than the microscopic, so more amount of substance that you are using for communication. I'll give you weird examples on this, okay? And the idea is one of the major applications that they are looking for this is to do something called targeted drug delivery, particularly for curing people with cancer. ربنا يعافينا ويعافيكم يعني. Okay, so cancer in general is a disease that happens at the cellular level. So the cell becomes disordered somehow, and the growth becomes uncontrolled, and then the person starts having a cancer. Okay, and typical treatment is by removing that part or part of the organ, and then curing the remaining, because they cannot remove all the cells, right? So curing the remaining part by injecting the chemotherapy or radioactive material that actually kills the cells. It kills more of the cancerous cells, but it still also kills the healthy ones. And that's why people who are going through chemotherapy, they actually suffer a degradation in their health until they stop the chemotherapy, okay? There's a new branch in medicine which is called targeted drug delivery, and what they want to do is at the scale, the nanoscale, the scale of the cell itself, they want to deliver the drug to a particular cell which is the one which is cancerous, without really touching the other healthy ones. And how they do that? Through releasing some vehicles inside the body. These are small protein molecules, and that's one example. Those protein molecules, they have some helical, the structure has something helical, and whenever you put whenever you interact with them with a chemical reaction, certain chemical material, this starts spinning, and it pushes the molecule to move in a certain direction, right? So now you can steer the molecule. Through what? Through sending chemical signals, right? Until you steer it to the cell that you want to kill, so that it goes into that cell and then kills the cell. So it's not only this, of course, on top of this, they put the medicine itself. So that is just the motor protein is just vehicle for movement. And on top of that, they put the active substance that's supposed to kill. The domain is very complicated. Look at it. It includes many things, but part of it is this ability to communicate with those carriers through chemical releases, okay? To give them commands, basically, okay? Another interesting idea is, you know, of course, that under seawater, you cannot really communicate using RF. If you want to send electric signal or electromagnetic signal under the seawater is conductive. So it's gonna absorb all the energy, and your energy is gonna be wasted. Nothing is gonna go on, especially if you go to deeper, like more depth under the sea. Same thing if you want to send a signal like through ground. So for example, very deep well, like the ones in oil and gas industry, and you want to send a signal down there, it's gonna be dissipated in Earth. Don't forget that Earth is ground, and that's the ground in your electric circuit that says always 0 voltage, no matter what you do, and that's true. Whatever energy you put into it, it's gonna absorb it and it's not gonna go anywhere, okay? I mean electric energy. So now what happens in the sea? Subhanallah, we were given the guidance by whales and dolphins, and they use the ultrasound or the acoustic signal to communicate together instead of electromagnetics. Again, what happens in deep well communication is that they use a very strange medium of communication. They inject into the driller, there is an outer cylinder, an inner cylinder, and then the driller is inside. And as it moves, this outer inner has a gap in between with mud inside it. It's a little bit viscous mud, but it's not completely liquid and it's not completely solid. And then they have the sensors attached to that drill to tell, for example, we have reached a very hard layer of rock, or we are now in sandy layer. They want to sense what's happening, and this information needs to be communicated up. What happens is the sensor is attached to a transducer that takes whatever information coming from the sensor and converting that into pressure pulses. So these pressure pulses go through the mud and you can sense them at the surface. So now you sense, for example, high pressure, low pressure, high, low for a few seconds. Then that means dot dash, and then you can read a particular signal, right? Or you can read a particular information. So that's another way you can think about communication. Anyways, most of the modern applications now also, or many of the, advancement in communication now is also targeting communication over the body or over the human body. And one example of that is, this is a bit of a graphic one, but sorry for that. In this case, they are attaching sensor to the brain itself. And then they close, and these sensors are used to either issue pulses to the brain in cases of ربنا يعافينا يعني الصرع والحاجات دي to control it اللي هو epilepsy, or sometimes to just read some information needed for the treatment later on. Even though we don't like this, and maybe I can hide it somehow because I'm getting you all, I don't know what to do. Anyways, but we all have heard about Neuralink of Elon Musk, right? So what is he trying to do actually? Does anyone know? Why? What's the announced application right now? Is it really to like educate people and?
No, to take their own information.
No, that's not the target announced now. It's very smart, by
Yeah,
the way.
but
I think this might be a future target.
Yes.
But you know how it's announced now? It's going to be what? It's going to be a
Increase
cure.
intelligence, I think.
No, it's going to be a cure for people who have quadriplegia. Quadriplegia are people who cannot move their hands or legs. So they are completely paralyzed, right? And what he's saying, and what he got an FDA approval on, is that he's going to implant those on the brain, and then they will have, instead of the spinal cord, which is supposed to carry that signal to the limbs, he's going to use wireless communication to devices attached to the nerve endings of the limbs. And through a machine learning algorithm that will take a while to develop actually, they will learn what signal is supposed to come from the brain when I am supposed to have the will that I want to move my hand. Because nobody knows exactly what's happening, right? When I want to move my hands, what does my brain exactly issue, right? And then carry that through wireless to the stimulator attached to the nerve on the limb, and then the limb will react accordingly. So imagine he selected people who are desperate, right? So those people, if you tell them, I'm gonna cut you and put a device, but you will be able to move your hands and legs, they will say, welcome, go ahead and try it, right?
Is they like have to first test it on the healthy people, like to see the
No, it's the other way around. They're gonna test it only on non-healthy people.
to capture what signals they use.
For that one, to capture, they will use probably learning through EEG, the external sensors that can be put around the head, but not to probe into the brains. He's not gonna find many candidates to actually go for that, right? So it's a very smart